Hello, everyone. My name is Thom. I'm the Vice President of Software and Cloud Services at Dwave Systems, and I'm here to talk to you today about practical quantum computing. I just wanted to begin by saying thank you to the GMIC Live Pro organizers for the opportunity to speak with you today, and I'm really excited to share with you some information about the technology, the types of applications that it's being used for, letting you know the access that is available online right now. And hopefully, if I share that excitement, you'll be interested in looking into it and really getting started at looking at creating your own quantum hybrid applications. Now, D-Wave Systems has been in business for a little over 20 years. And I've been with D-Wave a little over 18 years myself, with a background, initially working on building the quantum computers. And then I actually got out in the field talking with our customers and partners about what kind of problems quantum computers solve. And then my most recent career element of my work is our quantum cloud services and quantum application environment online called LEAP. And that's really about making it easier for all of us technologists and businesses to actually get access to quantum computers, to put them into application workflows, testing them at full scale, and to basically bring application value to our businesses leveraging quantum technology. And D-Wave prides itself on being really focused on getting to production applications and solving problems for businesses. In fact, we're just about to launch our next product, the Advantage processor, system, which has 5,000 qubits, and that's the first quantum computer that is really built for business. And I'm hoping to share that with you, and that you'll see that throughout the talk. So let me first start. D-Wave Systems is a pioneer in quantum computing systems and in commercializing them. And part of what's enabled us to do that is our approach with quantum annealing. Now, once you've decided that you want to use quantum mechanics to help you with information processing, you have to decide what model you're going to use so that you can use these phenomenal, fantastic quantum states and help them process information for you. So let me use a metaphor. And the metaphor is that we are working on an application where the challenge that we have, the information processing challenge, is to find the lowest point in a really, really large landscape. Now, these same problems can be approached by classical computers, and they're done by stepping through the landscape sequentially, walking through, finding our way downhill, and when we get trapped in local minima, then walking back uphill in order to be able to try to find another valley in the landscape that will be low. And this can be require both quite a bit of energy and be time intensive. So how does quantum annealing take the same type of problem and change it? So if you have a quantum computer with bits, so binary bits of information, zeros and ones, that can be quantum mechanical, so a qubit, it can be in two states at once. What that allows the quantum computer to do is that it can actually rain a tiny droplet of water on every point in the landscape. It can actually explore this enormous solution space in one moment. And then through an effect called quantum annealing, it can gradually localize that water so it's dripping off of the mountain peaks down into the valleys and collecting there. And at the end of the algorithm, it can actually point out where are the lowest valley or valleys in that landscape. And it's being able to leverage quantum mechanical effects like entanglement and superposition, allow it to search through this landscape much more quickly and with better energy efficiency. So if we were to talk about the size of the solution space, if we were using a classical computer, it might be able to step through 5 billion points in the landscape every second. And that might seem like a lot of very quick progress through the problem. But some of these solution landscapes can be have as many solutions as 2 to the 300, which is much larger than the estimated number of particles in the universe. So the fact that a quantum computer can search the whole landscape simultaneously and very quickly settle into these high-quality solutions is what makes quantum computing really attractive for solving problems in application today. So let me give you a little context of quantum computing as a space. in the past 20 years, quantum computing has been a combination of theory and experimentation, really accessible to a small group of experts in the scientific community who have been exploring different devices and how to link them together and get them to communicate with one another. And what's happened as D-Wave has been able to commercialize these quantum computers is that 2 years ago, a milestone was reached where some researchers at Texas A&M and at the NASA Ames Research Center who were developing classical algorithms to compete with quantum computers were able to find a benchmark problem where they found a 100 times speed up over the entire suite of state-of-the-art classical heuristics that they were developing. Now, that was 2 years ago. 1 year ago, D-Wave pioneered some work in quantum material simulation. So using its quantum processor to actually simulate the properties of quantum materials that had different structures than the quantum computer itself. And in so doing, managed to do some calculations about the properties of those materials 3 million times faster than the state-of-the-art classical solution. So that is really capturing what's exciting about quantum computing, is this opportunity to accelerate and disrupt some calculations by that large of a magnitude. So businesses and partners and independent software vendors are looking at how can we bring that capability to market and help our users out. So that's where we are right now, is looking at in-production applications, and we're working with forward-thinking businesses and partners in order to be able to bring them to a point where they're going to see customer advantage. So they're going to be able to use quantum computers in application and see better value than they would if they were using the other commercial technologies that they normally would in business. And in the longer term, that's also going to lead to scientific experiments that demonstrate that some of those advantages could only be obtained through quantum mechanical means in the future. Dwave Systems has currently a 2,000 qubit processor. And this system is about 3 meters wide, 3 meters deep, and about 3 meters tall. So a little bit taller than I am. And you can get access to a D-Wave 2000Q through our cloud-based quantum cloud services and application environment called Leap. This allows users to get immediate real-time access to the quantum computers, begin coding their examples, get access to the open source software tools, and start their experimentation and application development right away. The user interface you'll find is easy to use. It gives you a high-level dashboard and a set of user examples that will allow you to see, both demos that you can run just in your browser and programming examples that you can use so that you can modify those and learn about what kind of applications can be applied to this type of quantum computing. And Leap has been deployed in the US and Canada, 32 other countries in Europe, as well as Japan, Australia, and India, and it's continuing to expand globally. Now, one important milestone that took place at the end of last year was when Volkswagen basically ran the first in production quantum hybrid application. And in this, they demonstrated it at the Web Summit in Lisbon, where they were optimizing the shuttle buses for the conference using a quantum computer. So you can see in this photo one of the quantum shuttles that they used in Lisbon. So what they did is they partnered with organizations so that they could provide navigation information to each of the drivers. They could collect real information about the state of the traffic in the city and the routes of the drivers themselves, and then repeatedly call the quantum computer and re-optimize the routes of the buses so that they could minimize the overall congestion through the city as they were traveling through. And one of the bus drivers, who had 20 years of experience driving in Lisbon, commented that at one point the algorithm and the user interface suggested that he take a route he'd never taken before, and he was pleasantly surprised to find that he actually got through the traffic faster, and that was a big success. So it is, from my experience in the early days when we were producing our first devices, it's really exciting to see that we've really moved past a lot of the technology milestones needed and really entered into what does it take to deploy production applications that can call quantum computers and make use of their responses in a hybrid application using both classical and quantum technology to deliver value to its users. Here's another example with Denso, who is a very large automotive parts, systems, and components manufacturer that provides services and parts to automotive companies around the world. They are really interested in exploring what kind of new frontiers of applications are available by leveraging quantum computing. And in this study, they looked at their factory floors and particularly the routes that were taken of the automated guided vehicles. These are vehicles which use sensors to be able to move parts around the factory floor to the various locations that they're needed. In this study, they took the routes that they saw were available for these AGVs, and they ran a conventional optimization to move around the factory floor so they could see when were they moving, how frequently were they waiting, were they ever in danger of colliding with one another, and changing the how conservative they were so that they could make sure that the AGVs were safe. And what they found was that taking that application software and mapping it to a D-Wave quantum computing system with the classical program that they were running, they were actually able to generate this hybrid use case where they saw a 15% improvement in a reduction in the wait times that the AGVs were having when they were crossing one another's paths, while still maintaining and optimizing for the safety of the AGVs. And Denso is now going to be, moving forward, looking into new applications in mobility. Also looking at opportunities to look at, ride-sharing vehicles and taxis, so they can look at multimodal mobility challenges and optimizations in real cities to see what kind of solutions can be brought to their end users and customers. Recruit is a company in Japan that has been taking a really early move into quantum computing and looking at a variety of studies. And this is an example of looking at digital advertisements and looking at how to incorporate quantum optimization into the challenge of presenting ads to users when they're navigating in their browser online. For those of you who aren't familiar with digital ads, it's when you visit a website in order to read a news article or to search for some information online, there are opportunities for advertisers to present relevant advertisements to you, to present their products and information that you'd be interested in. And they get measured based on how frequently do people click on the ads. Now, maximizing click-through rate is an important measure for digital advertising. But in this case, Recruit Communications was looking at two other important components. One of them was budget pacing. So when you're choosing when to place your advertisements throughout the day, budget pacing allows you to consistently place ads to users all day long without having your algorithm consume all of your budget early in the day or at particular peak times. The second optimization they were looking at applying quantum computing to had to do with maximizing not just getting high click-through rate, but trying to reduce the volatility of the click-through rate that they were seeing in the digital advertisements. And when they were looking at their web services, they were, in their early studies, they were actually able to see a sales uplift in the web services that they were providing. Now, Toyota CRDL is another company that was interested in studying applications to do with mobility. So they looked at a traffic flow model of a city where they had streets going horizontally and vertically, and studied how are these optimized with traffic light systems as they run normally. And then how can we use a quantum computer and the type of optimization that it can provide in order to be able to optimize the configuration of the light signals throughout the city in one large optimization. And when they were able to do that, they were able to find that they could produce better solutions with that method on quantum annealing than when they were using conventional simulated annealing. Simulated annealing is a classical algorithm that can be used to produce optimizations and solutions to problems of this type. Groupnots is an organization in Japan who produce tools and methods to allow people to program with these advanced technologies more productively in their business applications. And they have created a set of programming tools called Magellan blocks, which allow users to be able to program and incorporate machine learning methods into their business solutions, as well as quantum optimizations. And as they've been looking at creating these Magellan blocks, they've been combining the ability to have data modules with optimization modules with application modules. So the optimization modules work on producing the high quality solutions themselves, and the application modules bring those optimization results into the application context. They looked at studying the routes of garbage collection through a neighborhood in Japan, and took a look at the grid and focused on optimizing the routes and the locations that they were going to be taking, tracking how the vehicles would be moving through that area. And particularly, they were trying to find if this sort of optimization can be done, we can be reducing inefficiencies, reducing our consumption of fossil fuels and the production of CO2 emissions so that we can make more sustainable cities. In this study that they conducted, they were able to take a route which was consuming about 2,300 kilometers of distance traveled by the trucks down to 1,000 kilometers, which they found was going to result in a 50% reduction in the amount of CO2 emissions, as well as the number of vehicles that were required being reduced to 59%. I'll switch my slides here. There we are. Sigma I is an innovative company in Japan which is looking at applying quantum computers and hybrid quantum methods to a variety of applications. And as COVID-19 has been impacting all of our lives, they've been looking at case studies and methods where they can apply this type of optimization to challenges that we're all seeing in society. They have a great website, and they've been posting example applications that they've been working on, and some of them are listed here. These include transportation optimization to medical centers, where we have a challenge of getting medical supplies from a variety of locations in cities, and then getting them out to their medical centers, and trying to make sure that that process is optimized and as efficient as it can be. They've also looked at diagnostic testing strategies in order to be able to help with the process of detecting and controlling the pandemic and being aware of where infections are taking place, as well as transportation logistics for different supply organizations. And they've also looked at studying and optimizing models for easing lockdown restrictions, trying to do that in a way that allows us to get as much of the benefits and freedoms of our lives back and our ability to work productively with one another, while also trying to maximize our effectiveness at controlling the impact of the pandemic and its potential spread among us. Here's an example of a company called Menton AI, which is looking at a biology application. So Menton is actually using Rosetta software to do protein design for medical applications from scratch. So rather than starting with existing proteins that are used in therapies and studying small changes to their structure, they can actually propose and calculate completely new protein structures, calculate how they're basically going to be, like how they should be designed in order to match the structure that they're looking at, and then go through an application workflow where they verify that it actually works, synthesize the proteins, and then actually take them to the wet lab for testing. And this company has synthesized some of the first quantum hybrid designed proteins ever in the world, looking at sidechain optimization and incorporating these methods that they've learned. And it's been a fantastic collaboration from the standpoint that they've really started early in the process to understand quantum computing technology and the types of problems that are suitable for it, as well as having their domain expertise, and then working on incorporating hybrid algorithms so that they can get application scale solutions quickly and basically begin focusing on their business, which is bringing value to their customers and creating protein designs which have high value. Now, I'm really excited to let you know that we're very close at D-Wave from launching our Advantage quantum processor. This will be the most connected and powerful quantum computing system that's available in the world. In fact, it will be the largest programmable quantum system that has ever existed. So the D-Wave 2000Q has 2,000 qubits in it, and this new processor will actually grow that system by 2.5 times with 5,000 or more qubits available and 35,000 interconnected couplings. So relative to our last product, that's more than 6 times as many interconnections within the processor. That should make it easier to map applications to the system and for it to get high quality solutions to those problems and be able to contribute to these hybrid algorithms. In the quantum material science studies that we've looked at, we've been able to go from an 8 by 8 lattice up to 15 by 15 by 12. So there's really a dramatic expansion in the size of the system. And that's really critical because in these applications, every time you double the size of the system, it's not that the problem gets twice as hard. It actually gets exponentially more complex. So this is really an application space where the complexity of the problems that we're approaching are rapidly outpacing the classical processing technology that we have. What's really interesting about these systems is that this is the largest superconducting circuit, integrated circuit that's ever been developed. In fact, even though the circuit is about the size of one of our thumbnails, there is about 110 meters of wiring in it. And we've been able to leverage innovations in our low noise fabrication to be able to improve the quality of the solutions that we're getting and really support hybrid applications. And there's a set of open source tools that D-Wave has called Ocean that you can use to begin programming and building these quantum applications. What's also really significant is that these systems that I'm showing you, in fact, there's a photo of one of these systems here in the lab, they consume about 25 kilowatts of power as they're processing. And you'll see in the photo on the right of your screen that there are 19-inch data racks there, which we use to house pumps and compressors and controllers for the quantum computing system inside. If one of those data racks was completely filled with classical processors, it would not be uncommon for it to consume about 100 kilowatts of power. So this entire system is in fact much lower power than a fully stacked data rack with classical computing technologies. But the other fascinating element about this is that the quantum processor itself inside the system, the chip consumes 1/10 of a millionth of a watt. And that's because the actual circuitry on the chip is made out of a metal that superconducts. It can actually flow currents through the metal without producing any heat. So the power consumption of the system is actually by the peripherals, those pumps and compressors, and those remain constant as we move between these processors. So between the 2,000 qubit system and the 5,000 qubit Advantage quantum computer that's coming out this year, the actual power consumption of the chip and of the overall system will remain flat. And that's one of the fantastic concepts that can be realized with these quantum computing technologies, And if we can find just the right fit for these in our applications, we can actually probably uncouple this massive unsustainable growth in the amount of energy we need in order to be able to compute these calculations, because quantum computers can do those much more efficiently. So I'd encourage you today, with the things that we've talked about, if you're as excited about quantum computing as I am, to get started right now. Take a look at our open source tools, go to Dwave's website and check out our LEAP platform for the cloud services and the quantum application environment, and begin building your hybrid quantum applications today. And one important point that I'll make is that it's often the case with like brand new technologies where we think, I guess I'm going to have to figure out when I need to find like just the right time to incorporate this new technology. But just like the hybrid cars that we drive around on our streets today, there are algorithms which can give us all the benefits and flexibility of classical computers today and incorporate these quantum solutions and hybridize the two technologies together. There is 10 years of research that's been done to highlight what the two technologies do best and how to make use of them in a complementary way. And what that means is that by beginning your hybrid quantum application development right now, you're actually bringing your business, this kind of technology into your business in a way where as it powers and develops more, as the algorithms become more efficient and the processors become larger, that application gets the benefit of the technology without having to lose any of the benefits of classical solutions that are available to us as well that can be run alongside. So I hope you've really enjoyed the presentation. Thank you very much for taking the time to watch, and I hope you're just as excited as I am to take a look at practical quantum computing and to potentially get started building your quantum